So, yesterday we had introduced the concept of jointly distributed random variables. So, because many times we will be interested in recording the numerical characteristics of several phenomena in one random experiment. For example, for a newborn child we will be interested in recording its height, weight and pulse rate at birth. A doctor records several characteristics of the patient who visits him for certain disease. The performance of a student is in a semester during a course is measured in terms of its marks in, say, homework assignments, his performance in mid semester examination, his performance in the end semester examination, etc. We have seen that the types of jointly distributed random variables, some of them may be discrete, some of them may be continuous, all may be discrete, all may be continuous, some may be mixed, etc. In particular, when we are considering a jointly distributed random variable x y, we have considered two specific cases where both x y may be discrete, such as marks of the students, or both may be continuous, for example, height and weight of a child at birth. So, in the case when both of them are discrete, we have a probability mass function, and when both are continuous, we have a probability density function. We have seen the description of this, and using this we can calculate any probability statement regarding the joint distribution of x and y, or marginal distribution of x and y, or conditional distribution of x and y. Next, we discuss the concept of independence of random variables. So, we say that random variables x and y are independently distributed if the joint CDF is equal to the product of marginal CDFs at all points. So, basically, if we do not make use of the CDF, we should be able to say like that, that if we are considering a set in the two-dimensional plane where B can be expressed as product of two sets A1 and A2, where A1 is in the space of x values and A2 is in the space of y values, then this should be equal to probability of x belonging to A1 and into probability of y belonging to A2. If that happens for all combinations of this type of sets, then they are independent. However, this condition is equivalent if we state it in terms of the cumulative distribution function. In particular, if x and y are discrete, then x and y are independent if Pxy is equal to Pxx Pyy for all xy belonging to x cross y. In case of continuous random variable, if x and y are continuous, then the condition for independence is the joint PDF is equal to the product of marginal PDFs. Let us take some examples. Let f(x,y) be equal to say 1, 0 less than x less than 1, 0 less than y less than 1 and 0 elsewhere. Now, this is a jointly distributed continuous random variable. Let us consider say f(x). So, we will be integrating with respect to y from 0 to 1. So, we get 1 and similarly, if we integrate with respect to x from 0 to 1, we will get 1 and of course, 0 elsewhere. So, you can easily see that the product of f(x)(x) and f(y)(y) is equal to f(x)(y)(x)(y). This condition is satisfied for all x and y. So, x and y are independent. So, this may be considered as a arrival timings of a passenger to the railway station between any time from say 7 a.m. to 8 a.m. and y may denote the arrival time of the train between 7 a.m. to 8 a.m. So, both may be independently distributed and this could be the one of the possible distributions. Let us take another example. Suppose probability x is equal to 1, y is equal to 1 is 1 by 4, probability x is equal to 1, y is equal to 0 is 1 by 4, probability x equal to 0, y is equal to 1 is say 1 by 4, probability x equal to 0 and y is equal to 0 is say 1 by 4. So, the joint distribution of x and y is given by this. Let us look at the marginal distribution of x. So, what is probability of x equal to 0? It is obtained from summing the probability of x equal to 0, y equal to 0 and probability x equal to 0, y is equal to 1, that is equal to half. Probability x equal to 1 in a similar way, it is equal to the sum of these two probabilities, again it is half. If we look at probability of y is equal to 0, that is the sum of these two probabilities, that is half, and probability of y is equal to 1, that is the sum of these two numbers, that is again half. So, we can see here that the condition that pxy xi yj is equal to px xi py yj is satisfied for all xi yj in the range of x and y random variables. So, x and y are on the other hand, if we consider a distribution such as f(x,y) is equal to 10xy square, where x and y are satisfying the condition that 0 is less than x less than y less than 1. Then the marginal distributions of x was 10 by 3 x into 1 minus x cube and the marginal distribution of y is 5 y to the power 4, 0 less than y less than 1. So, you can see that the product of f(x) into f of y is not equal to f(x,y), because the product here will give you 50 by 3 x into 1 minus x cube into y to the power 4, whereas f(x,y) is 10 xy square. So, the condition is never satisfied. So, x and y are obviously not independent. If we consider another problem, say f(x,y) is equal to 1 by y for satisfying similar condition that 0 less than x less than y less than 1, then the marginal distribution of x is minus log of x and the marginal distribution of y is uniform. So, once again you can see that the product of these two does not give 1 by y. So, the distributions are not independent. So, and the main important role of the condition of independence is that it helps us to obtain the joint distributions for independently distributed random variables. Many times what happens that we know that these phenomena are independent and we know the individual distributions. Now, in order to study certain characteristic of the joint distribution, we can obtain the joint distribution by simply multiplying the two distributions, because in general marginal distributions do not give the joint distribution. The joint distributions give the marginal distributions, but the converse is not true. However, if the random variables are independent, then simply by multiplying the marginal distributions we can get the joint distribution. Therefore, this is a quite useful concept. Now, let us look at the concept of expectation in case of joint distributions. So, let g x y be a measurable function of x and y. So, we define expectation of g x y, that is equal to, if x and y are discrete, it is equal to g x I y j p x y x I y j for all x I and y j in the range of x cross y. This is if x and y are discrete with PMF p x I y j. Now, this is valid provided the series is absolutely convergent. Provided the given series is absolutely convergent. In case x and y are continuous with joint PDF say f x y, then we define expectation of g x y as double integral g x y f x y dx dy, or this could be dy dx also, provided the integral is absolutely convergent. Here the range of integration is over the range of the density, whatever be the appropriate range of the density here. So, in particular we can consider given random variables x y, we can define expectation of x plus y, expectation of x minus y, expectation of log of x square y, any type of function of the random variable x and y, we can find out its expected value. Now, in particular we will be concerned about product moments. So, we define mu r s prime as expectation of x to the power r y to the power s. This is r sth product moment. Now, here this is non-central moment, as we had seen in the univariate case also, we can define central and non-central moments. So, in particular we can consider mu 1 1 prime, that is equal to expectation of x into y. If we consider mu 1 0 prime, that is expectation of x, that is the mean of x or the expected value of the random variable x. Similarly, if we consider mu 0 1 prime, that is equal to expectation of y, that is equal to the expectation of random variable y. Now, using this mu x and mu y, we can define product moments which are central. So, we can talk about mu r s, that is equal to expectation of x minus mu x to the power r, y minus mu y to the power s. Now, if we consider the special case r is equal to 1, s is equal to 1. So, this is in general r sth central product moment. So, if we consider both r and s to be 1, that is expectation of x minus mu x into y minus mu y, this is called the covariance between x and y. We can further simplify this, we can write it as expectation of x y minus x into mu y minus mu x y plus mu x mu y, that is equal to expectation of x y minus. So, now here if we take expectation, this is mu x mu y minus mu x mu y plus mu x mu y. So, this term cancels out and we are getting, we can use this notation mu x y here, or mu 1 1 prime minus mu 1 0 prime mu 0 1 prime. We can further see the effect of independence on the moments. If random variables x and y are independent, then expectation of x to the power r, y to the power s, this will become expectation of x to the power r into expectation of y to the power s. Similarly, expectation of x minus mu x to the power r, y minus mu y to the power s, that will become expectation of x minus mu x to the power r, expectation of y minus mu y to the power s. To see this, let us prove a general result regarding the independent random variables. Let x and y be independent random variables. Then, if we are considering expectation of a product function, then this is equal to product of the expectations. Let us assume that x and y are continuous with joint PDF fxy and marginal PDF say fx and fy. So, since x and y are given to be independent, we have fxy is equal to fx into fy for all xy. So, now consider expectation of gx into h of y. So, of course, these statements are valid provided these expectations exist. So, let us consider expectation of gx into hy. So, by definition of the expectation, it is equal to gx into hy f xy xy dx dy or dy dx. Since the random variables are independent, we can make use of the condition of independence. That means, this is equal to gx into hy fx into fy dx dy. Now, this is nothing but the product of the integrals gx fx dx and hy fy dy, which is nothing but expectation of gx into expectation of hy. So, the expectation of a product is equal to the product of expectations in case of independent random variables. A similar proof can be given in case the random variables are discrete, because here the integrals can be replaced by the summations and the density function can be replaced by the mass function. The proof is little bit involved in the case of mixed random variables, and when one of them may be discrete or continuous, etc. So, in particular, if gx is x to the power r and hy is y to the power x, so expectation of a product moment is equal to product of the individual moments, and this statement is valid for non-central as well as central moments. Now, if we make use of this condition on the first central moment, first central product moment, which is we call as the covariance, then expectation of x into y will be equal to expectation x into expectation y, and therefore, covariance term will become 0. So, we have the consequence of this above theorem, that if x and y are independent, then covariance of x and y is 0. Using the covariance, one defines the coefficient of correlation between x and y. We denote rho x y, that is defined as covariance between x y divided by standard deviation of x into standard deviation of y. We can use the notation sigma x y divided by sigma x sigma y, where sigma x square was the variance of x and sigma y square denotes the variance of y. Now, the question arises that what this correlation coefficient between x and y represent. So, we claim that this gives a measure of linear relationship between the random variables x and y. So, in particular, let us consider, say, random variables u and v with, say, expectation of u is 0, expectation of u square is equal to 1, expectation of v is equal to 0, expectation of v square is equal to 1. If we consider these two random variables, consider the term expectation of u minus v whole square. Now, naturally this is greater than or equal to 0, being the average value of a non-negative term. Now, this will imply expectation of u square plus v square minus 2 u v is greater than or equal to 0. Substituting the value of expectation u square and expectation of v square as 1, this relationship is reducing to expectation of u v is less than or equal to 1. Similarly, expectation of u plus v whole square is greater than or equal to 0. This yields expectation of u square plus v square plus 2 u v is greater than or equal to 0. Once again, substituting the values of expectation u square and expectation v square as 1, we get expectation of u v greater than or equal to minus 1. So, we have got that expectation of u into v lies between plus 1 and minus 1, provided expectation of u and expectation of v is 0 and expectation of u square and expectation of v square is 1. Now, we can consider when the equality will be attained. So, here equality at 1 will be attained when expectation of u minus v whole square is equal to 0. Now, expectation of a non-negative random variable is 0 if and only if the random variable itself is 0. That means, u must be equal to v with probability 1. In a similar way, the equality at minus 1 will be attained if u is equal to minus v with probability 1. Let us consider the expressions for this. Here expectation of u v is equal to 1 if and only if probability of u is equal to v is equal to 1, and expectation of u into v is equal to minus 1 So, now let us take for any random variables x and y, let us use the notation that expectation of x is equal to mu x, expectation of y is equal to mu y, variance of x is equal to say sigma x square and variance of y is equal to sigma y square. Define u is equal to x minus mu x by sigma x, v is equal to y minus mu y by sigma y. So, if we take expectation of u, this is equal to expectation of x minus mu x by sigma x, and by the linearity property of expectation, it is expectation x minus mu x by sigma x, that is simply 0. If we consider expectation of u square, that is equal to expectation of x minus mu x square by sigma x square. Now, the numerator here is simply variance of x, that is sigma x square, so it is 1. So, in a similar way you can see that expectation of v is 0 and expectation of v square is 1. So, if we make use of the inequality that we have proved here for u v random variables with the property that expectations are 0 and the expectation of the squares are 1. So, we get expectation of u v between minus 1 to 1. Now, for any random variables x and y, when u and v are defined like this, what is the expectation of u v representing? So, expectation of u v is equal to expectation of x minus mu x by sigma x into y minus mu y by sigma y. So, the numerator here is simply the covariance term between x y divided by the standard deviations of the x and y, that is the correlation coefficient between. So, for any random variables x and y, the correlation coefficient lies between +1 and -1. The least value is -1 and the maximum value is +1. Now, rho x y is equal to 1. So, we look at the conditions for attaining the equality. Expectation of u v was 1 if and only if probability of u is equal to v is 1. So, this will be satisfied if and only if probability that x minus mu x by sigma x is equal to y minus mu y by sigma y is equal to 1, or you can say probability that x is a linear function of y, that is x is equal to some a times y plus b, where a is a positive number because sigma x by sigma y. Similarly, rho x y is equal to -1 if and only if x minus mu x by sigma x is equal to minus y minus mu y by sigma y is equal to 1, or probability that x is equal to a y plus b is equal to 1 if a is negative. So, this condition that x is equal to a y plus b, where a is positive, this is known as that x and y. So, we can write it that x and y are perfectly linearly related in positive direction, that is x is equal to a y plus b for a positive, and probability of this statement is 1. And if we say probability of x equal to a y plus b is equal to 1 where a is negative, then we say that x and y are perfectly linearly related in negative direction. Now, this gives a interpretation for the coefficient of correlation. So, we can see that in general coefficient of correlation lies between -1 to +1. The bounds -1 and 1 are attained. So, -1 is attained when there is a perfect linear relationship in a negative direction, or you can say perfectly negatively linearly related, and the equality at 1 is attained when it is perfectly linearly related in the positive direction or perfectly positively linearly related. So, in general any value between -1 to 1 denotes the degree of the linear relationship between random variables x and y. Suppose I say the correlation coefficient is equal to 0.7, that shows that there is a good positive correlation between x and y, and here the relationship is of the linear type. If we say rho x y is equal to -0.3, it shows that there is a lower degree of negative linear relationship between the random variables x and y. When rho x y is equal to 0, we say that the random variables x and y are uncorrelated. Now, here uncorrelated means that the linear relationship is not existent between random variables x and y. So, we can interpret these statements as so correlation coefficient is a measure of linear relationship between two random variables. If rho xy is 0, we say that x and y are uncorrelated. At this point, it is important to understand the difference between uncorrelatedness and independence. If we say that the random variables are uncorrelated, it does not mean that they are independent. Of course, if x and y are independent, it will imply uncorrelatedness, because if x and y are independent, then covariance term is 0, therefore correlation term will also be 0. So, we have the following result: if x and y are independent, then rho xy is 0, but the converse of this is not true. So, proof is of course obvious that if x and y are independent, then covariance term is 0 and therefore the correlation term is 0. Let us look at the converse of it. Let x and y have joint PMF as x is taking values 0, 1, y is taking values -1, 0 and 1. The probabilities are 0, 1 by 3, 0, 1 by 3, 0, 1 by 3. So, here we consider say expectation of x. So, here you can calculate the marginal distributions by adding the rows and columns. So, the marginal distribution of x is 1 by 3, 2 by 3. The marginal distribution of y is obtained as 1 by 3, 1 by 3, 1 by 3. So, expectation of x is equal to 0 into 1 by 3 plus 1 into 2 by 3, that is equal to 2 by 3. If we look at expectation of y, that is equal to -1 into 1 by 3 plus 0 into 1 by 3 plus 1 into 1 by 3, that is equal to 0. If we look at expectation of x into y, so we look at all the possibilities of the x and y values here. So, x is 0, y is -1 with probability 0, plus x is 0, y is 0 with probability 1 by 3, x is 0, y is 1 with probability 0, x is 1, y is -1 with probability 1 by 3, x is 1, y is 0 with probability 1 by 3, plus x is 1, y is 1 with probability 1 by 3. You can see these terms vanish. We are getting -1 by 3 and plus 1 by 3, so it is 0. Therefore, covariance term is 0 and consequently rho xy is 0. But we can see here that the product of the marginal distributions, for example, p x 0 and py0 both are 1 by 3, but pxy, so let us write here px0 is 1 by 3, py0 is 1 by 3, but if we consider pxy00, that is also 1 by 3. So, x and y are not independent. So, they are uncorrelated, but not independent. Now, this further brings out the contrast between the concept of independence and correlatedness. So, independence simply means then that the random variables, or you can say the observance of the two phenomena, has nothing to do with each other. That is, one phenomena which yields the random variable x and the phenomena which yields the random variable y, they are totally independent. Whereas, the correlation gives a degree of linear relationship between the random variables. So, if they do not have a linear relationship, the random variables may become uncorrelated, but that does not mean that they are independent. For example, even in this problem, it may happen that x is actually y square, because the probability that x equal to 0 is same as probability y is equal to 0, and probability x equal to 1 is sum of probability y is equal to minus 1 and probability y is equal to 1. So, this could be a non-linear relationship. So, let us take up a few examples for calculation of the covariance and correlation term. So, let fxy be equal to x plus y for 0 less than x less than 1, 0 less than y less than 1 and 0 elsewhere. In order to calculate the coefficient of correlation, we need the first and second moments of x and y and also the first product moment of the joint distribution. So, expectation of x into y, that is equal to double integral x y into x plus y dx dy 0 to 1. So, this is simply integral of x square y plus x y square, which we can easily evaluate, and it is equal to 1 by 6 plus 1 by 6, that is equal to 1 by 3. In order to calculate the moments of x and y separately, we can make use of the marginal distributions. So, you can see here that this will be equal to x plus half for 0 less than x less than 1, and similarly the marginal distribution of y will become y plus half for 0 less than y less than 1 and 0 elsewhere. The distributions of x and y are same. So, it is enough if we calculate the moments for one of them. So, expectation of x becomes the integral of x into x plus half from 0 to 1, which is obviously 7 by 12. So, the same value will be expectation of y, and expectation of x square likewise can be calculated. That is equal to 5 by 12, same as expectation y square, and therefore, variance of x, that is equal to expectation of x square minus expectation of x whole square, that is equal to 11 by 144, that is sigma x square and sigma y square. So, correlation coefficient is then equal to 1 by 3 minus 7 by 12 square divided by 11 by 144, which after simplification is minus 1 by 11. So, this means that there is a low degree of negative linear relationship between the random variables x and y. We can take up some example which we read yesterday. So, let us consider, say, f x y is equal to, say, 2, 0 less than y less than x less than 1, 0 elsewhere. Here suppose we want the distribution of x, then it is equal to integral with respect to y 2 dy from 0 to x, that gives 2x. So, expectation of x is equal to 2x square dx from 0 to 1, that is 2 by 3. Expectation of x square is equal to integral 2x cube dx 0 to 1, that is equal to half. Therefore, sigma x square, that is variance of x, is equal to half minus 4 by 9, that is equal to 5 by 18. Sorry, this is not 5 by 18, it is 1 by 18. So, we are able to calculate the mean and variance of the distribution of x. Similarly, let us calculate the marginal distribution of y, that is integral 2 dx from y to 1, that is equal to 2 times 1 minus y for 0 less than y less than 1, 0 elsewhere. So, expectation of y is equal to integral 2 y into 1 minus y dy from 0 to 1, that is equal to twice y. So, that is y square, that is 1, minus 2 y square. So, that is 2 by 3, that is equal to 1 by 3. Expectation of y square will be equal to 2 y square 1 minus y dy integral from 0 to 1. So, once again 2 y square. So, y square is integrated to y cube by 3. So, this is 2 by 3 minus 2 y cube. So, y cube is integrated to y to the power 4 by 4. So, that is 2 by 4, that is half. So, it is equal to 1 minus 4 minus 3 by 6, that is 1 by 6. So, we can calculate the variance of y, that is equal to 1 by 6 minus 1 by 9. So, that is equal to 1 by 18. Now, we have calculated the means and variances of the random variables x and y. In order to get the correlation coefficient, we need the product moment also. So, expectation of x into y, that is equal to 2xy. Now, here we can choose the order of integration, we may do dy dx. The range of y is from 0 to x and the range of x is from 0 to 1. So, this is equal to 2 times integral 0 to 1. Now, firstly we are integrating with respect to y. So, we get y square by 2. So, this term cancels out and that gives us x square. So, we are left with x cube dx, that is equal to 1 by 4. So, covariance term between x and y, that is equal to expectation of x y minus expectation x into expectation of y, that is equal to 1 by 4 minus 2 by 3 into 1 by 3, that is equal to 1 by 4 minus 2 by 9. So, once again it is equal to 1 by, so 9 minus 8 by 36, so 1 by 36. So, the coefficient of correlation is equal to 1 by 36 divided by 1 by 18. Both variances of x and y are 1 by 18. So, sigma x into sigma y will be 1 by 18. So, it is equal to half. So, this shows that there is a moderate degree of relationship, moderate degree of positive linear relationship between the random variables x and y. We also introduce the concept of the joint moment generating function between the random variables x and y as follows. Joint moment generating function between x and of x and y. So, we use a notation m x y at the point s t. It is expectation of e to the power s x plus t y, provided the expectation exists in a neighborhood of 0 0. At 0 0 this always exists and it is equal to 1. So, in a neighborhood of 0 0 this should exist. Now, the nature of this term is nice, it suggests certain properties. For example, it is equal to expectation of e to the power s x into e to the power t y. So, the first thing that we observe that if the random variables are independent, it will become product of the expectations of e to the power s x and e to the power t y, which are nothing but the individual moment generating functions of x and y. However, because of the uniqueness property of the MGFs, we have a stronger result here. X and y are independent this implies and implied by that m x y s t is equal to m x s m y t for all s t. In order to prove this, let us consider say the case of continuous random variable. With joint PDF say f x y and marginal PDFs say f x and f y. Now, here let us notice that if the random variables are independent, then this expectation of a product will be equal to the product of the expectations. So, the joint MGF will be equal to the product of the individual or marginal MGFs. Let us look at the converse. Let this one relation be true, then this implies that integral e to the power s x plus t y f x x y dx dy is equal to integral e to the power s x f x dx into integral e to the power t y f y dy for all s t. Now, the right hand side we can write as product of the two integrals can be written as a combined integral e to the power s x plus t y f x into f y dx dy. Now, note here the left hand side denotes the joint MGF of random variables x and y when the PDF is fx y. The right hand side denotes the joint distribution, the joint MGF of the random variables x and y when their joint distribution is given by fx into fy, and this statement is true for all ST. So, by the uniqueness of the MGF, the two densities must be same. So, the left hand side denotes the moment generating function of a random variable x y with joint PDF fxy xy, whereas the right hand side denotes MGF of a random variable with joint PDF fx into fy. As they are identical, by the uniqueness of MGF, we conclude that the distributions must be the same. So, we should have fx y x y is equal to fx into fy for all x y, that is x and y are independent. So, this is quite a strong property, and that is true because of the uniqueness property of the moment generating functions. So, independence of random variables can also be proved through the consideration of the joint MGF. We end this one with another result. If x and y are independent, then m x plus y, that is the moment generating function of random variable x plus y, it is equal to the product of mx and my. The proof of this is almost trivial. The left hand side is expectation of e to the power t x plus y, and so if independence is there, this can be written as t x into e to the power t y, which will become expectation of e to the power t x into expectation of e to the power t y, which will be this term and this term respectively. This result is extremely useful in obtaining the distributions of sums of various random variables, because if we know the MGFs of those random variables, then we can identify the distribution of the sum by identification of the MGF of the sum as the MGF of certain random variable. So, we will consider the bivariate normal distribution in the next lecture.